Except all of that was wrong.
So let's pick up where we left off. So if you remember, shut up! If you remember right before the midterm, we had finished building out our grammar, our statement-based grammar. We're already dealing with the lexical analysis. What do we need to change in our lexical analyzer to handle things like for statements, if statements, things like that? Right now, our code looks like this. My first program, .simon. Okay, so right now our code looks like this. This is what our input looks like. Do we need to change anything with our lexical analyzer to allow it to handle things like if statements and for loops and things like that? So don't guess. Think about it.
Yes. Pretty sure we got it correctly.
How would an if statement, let's just use this production right here, how would this guy be handled in terms of lexical analysis? What would you expect this guy to get broken into? Would you expect there to be a lexeme that's for an if expression? Or would you expect there to be a... What's this guy going to be? What's if going to be? Okay, it'll fall into the category of a reserved word, but before it's a reserved word, what kind of animal is it? Is it a symbol? It'll be an identifier. Okay, so if will be picked up as an identifier. Then opening curly brace. Okay, but it'll also be picked up as, will it be an identifier, or it'll just be a, what will our lexical analyzer depict it as? Here is our, do we do it inside of language reference? So we have such thing as math ops, Boolean ops, types. We have our reserved words, which all those guys fell into, and our literal. So is there a difference between something that gets, let's go and look at our, get some source reader, right? Lexical Analyzer. So Lexical Analyzer handles things like an identifier. These are variables, right? It handles things like math operators, Boolean operators, literals, reserved words, and then types. So something like an if, I guess we could do it from our grammar here. This will be reserved word, reserved word. What about our expression? This is going to be something else that's an expression, correct? So what's our language of expressions? Yeah, it's a type expression. Expression can be a literal, an identifier, a math expression, or a Boolean expression. So those guys are going to have information within them that allows us to then create lexemes that are either identifiers, math operations, Boolean operators, so on and so forth. Okay, and then statement's going to zip back through this and do it again. So does our lexical analyzer currently work for our entire grammar? I think it should. Okay, so after we've got our token stream and after we've lexically analyzed it, we have a collection of lexical tokens, right? Now we need to put it into a syntax tree with lookahead. And that's what we need to start thinking about now. As we start processing our language of statements, remember Java, well, the language that we've invented, Simon here, is a Java-like language that is a collection of one or more statements. Correct? All right. So how do we create our tree structure with lookahead? Remember the difference between lookahead and our original syntax tree structure. With lookahead, we identify what the first part is and then determine what should come next. That allows us to identify syntax problems, right? That's kind of how, if we look at something like Xcode or Eclipse, how they're able to treat, they can highlight things in red when we've made a syntax error instantaneously. Because they have a constant, almost like a subcompiler going on at all times. It's not actually running the Java compiler to test that. It has its own version of a tree analyzer based off of the grammar of Java. So it can determine if what you just typed is a legitimate thing to type. Does that make sense? Okay. So we need to build a tree structure that starts going through our lexical analyzer, looking at each lexeme and deciding, is this guy the start of a new statement or is it an existing statement? Are we going to have a tree structure for each statement? Is that a fair statement to make, pun intended? Every single time we run into a statement, we're going to have a tree, correct? Okay. So if we look at our code here, as our example, this guy is one of our type statements, correct? Type, identifier, semicolon. It's one of those guys. So we're going to have a tree that's going to expect type, followed by an identifier, followed by a semicolon. How do we know that's what we're expecting? If we run into something that starts with an int, something like that, that's one of our type guys, right? So it's either type, it's either this kind of statement, or this kind of statement. That's it. We've defined what our types are. Int, char, and boolean are our types in our current language. So if we run into a token, well, lexeme, that is a type, and we did identify those, we have a type lexeme right there. So if we run into a lexeme that is a type, we know right off the bat that we're either dealing with this production or we're dealing with this production. So now we need to read the next. We don't know what the lookahead is until we've narrowed it down to exactly one thing that it should be. Correct? All right. So if we've read in a type, let's start doing this. I think we gutted our syntax analyzer last time, right? So this is our tokens inside of Lex Tokens. So for each of these, we need to determine what kind of token it is. Is it one of these? Was it one of these? Is it one of these, or these? So let's just use our simple example of type to start off with, just because that happened to be what came first in our language. How are we going to determine if a particular lexical token is a type token? Remember, those guys look like this. That's what the string would look like. Okay, well, it's always going to start with something like that, correct? Can I check for that pretty easily? How would you check to see if the lexicon you're currently looking at indeed starts with less than type colon?
Split on colon and check the first 20.
Could do that. It'd be even an easier way of doing it. Could use index of. So couldn't we say if lt dot index of type colon is equal to 0? That means we're looking at a type lexicon. Now, remember, last time we wrote this little decompose Lex token thing. Why did we write this? It allowed us to split things into two parts. And then we asked the question, why did we put it into lexicons if we needed to split it back out into its individual parts? Right?
Right.
So what was the answer to that?
Wrong.
Why did we put it into lexical tokens if we're going to ultimately need to mine the values back out of it?
Said so. We had a solution to that.
I didn't just say so. The book said so too.
And it was agreed. Follow blindly, so I don't know. Tells you what kind of token it is.
Okay. It is useful. It is useful to have that piece of information. Just because something is useful doesn't necessarily mean that it won't be hard work to then go and get it back out. So think about this as you packed up your house. Okay, it's useful to have all your stuff separated into boxes and all that stuff for transporting it someplace else, correct? But at some point, if you want to get the stuff out of the box, you're going to have to open the box and take the stuff out. We needed the things in lexicons so that we can store them generically and deal with them at a generic level. For instance, anything that starts with a type. Before we had them as lexicons, we didn't know something started with a type. What did we have to do? We had to say, well, does it start with the word int or the word char or the word boolean? And what happens if we then go to add another type to our language? Well, then we need to go in and add an additional if statement. Well, the way we've written it right now, we have a language reference class that has all of our types in it. If we want to add a new type like dog, we can have a dog type. We can easily do that. And then all of a sudden start creating variables of type dog. All right? So it's not that we packaged it up and then we're unpackaging it. It's that we categorize them into generic categories, and the lexicons allowed us to do that. But now we're at the point where we actually need to get at those pieces to know what we're dealing with. What does our decomposed Lex tokens do? It takes in a lexical token, it creates an array, splits it on the colon. This is what Coleslaw was saying to do. Then we took everything but the less than sign of the first part, and we took everything but the closing sign of the second part. Does that make sense? That gave us our two pieces, and then we returned that string array. So if we have that, we're going to create a string array called cur token. No, let's call it cur parts. Let's just call it parts. Perfect. So we're going to say parts is equal to this dot decompose Lex token of LT. And that's going to give us our two-dimensional array, or our two-bucket array. Now we can say if parts at bucket 0 dot equals type. If that's a true statement, we're dealing with a type expression of some type, correct? Of some kind. But as of right now, we don't know if it's this guy or if it's this guy. So what do we need to do next? We need to take another step further. We can't look ahead yet because we don't know what's coming next. We know that it's either going to be a sign. It's either going to be an identifier or it's going to be an assigned expression. And what's an assigned expression? Don't we have an assigned expression somewhere in here? What the heck are assigned expressions? Oh, this guy. Yeah, this guy's an assigned expression, but that doesn't really tell us what an assigned expression is, does it? Yeah, I think we need to define what an assigned expression is. So we need another slide. We have expressions. So expressions could be literals, identifiers, math expressions, or Boolean expressions. Could we throw an assigned expression in there for types of expressions? What does a signed expression look like? A signed expression would look like an identifier followed by an equal sign followed by an expression. Yeah. Okay. So we're going to add an assigned expression to our grammar of expressions. Assigned expression is going to be an identifier followed by an equal sign followed by an expression. Even that might break. Expression could be a literal, an identifier, could be a math expression, a Boolean expression, or another assigned expression. We don't want it to be another assigned expression. So we're going to treat assigned expressions as their own one-off. So an assigned expression is an identifier followed by something that is an expression, followed by a semicolon. Actually, we'll leave the semicolon off. We're going to say this guy is an identifier followed by an equal sign followed by expression. Why did we leave the semicolon off, Joey?
Because it was. I'm sorry, I can't answer this question.
Assigned expressions are going to be one of our statements, right? And one of our grammars of our statement says we have an assigned expression followed by a semicolon. The semicolon is what makes it a statement. Does that make sense? So the semicolon isn't part of the expression itself. It's part of the statement version of an assigned expression. Okay. So once we see a type, we need to look ahead for one of two things. Now we've got to start thinking about how does the look ahead work. If you remember back when we were looking at this in the book that we had on here, it tried to match one of two things. So at this point, we don't know which we should see next, but couldn't we try to match both, knowing that we're only going to match one? So if I run into a type, if I start off with a type, there are two things that it could possibly be coming next. It could either be an assigned expression or it can be a identifier. Should we have the ability to match identifiers and match assigned expressions? Should we have the ability to match any of these guys? Should we have the ability to match any of these guys? any of these guys. So the question, and this is a development question we need to ask, do we haphazardly take one more step forward to see if we can further identify? So really this is, I guess, a development decision. Do we say there's two possibilities, let's try to match both, and one of them we know is going to come back? Well, one of them will come back good. At most, one of them will come back good. It's possible if it's a syntax error, both of them came back false. I couldn't match either of these because the person who wrote the code wrote crap. Does that make sense? Could be a syntax error. But at most, we should have it come back true. I was able to match this for exactly, or at most, one of our next parts. That's one way we can do this with the Lookahead. Similarly, we could just read in the next lexin and say, what are you? And make the decision from there. One is kind of a recursive solution. The other one is kind of an iterative solution. Either way, I'm going to need to read in the next lexin if I'm stuck with a type expression. What is the next lexin going to look like? So what do you think? Do we try to match the next guy and say, this guy's either this or this, so let's match them both, knowing that at least one of them is going to scream? Or do we look ahead and manually check to see, is it A or is it B, to determine how to match the rest of it? Opinions? Go ahead.
I like the second idea.
Okay. Any particular reason?
Because it's probably what I would do.
Okay.
More of an opinion kind of a thing.
Okay, I'm fine with that. All right, so if we go with the second, we're going to need to determine how many things this particular guy matches. So if I'm looking at a type, if what I have so far is a type matches two things. How do I programmatically figure out that if I'm in this if statement, one of two things is matched? I need to programmatically do it. That way I can easily change my structure through my language reference. We know as human beings that we can look at this documentation and say, oh, well, it's either got to be this guy or this guy, because those are the only two that match types. How do we programmatically do that?
Wouldn't we do that in the source reader? Getting out like a get type, or the rest of the type, or get if statement, if we're to do if statements. Error.
Well, this is for the tokenizing.
Right.
I don't think we have anything in there right now. Is it unreasonable for us to just say, since it's a type, we know it can match two things? At what point do we automate our grammar? I mean, we have two options here as well. We can say we let our grammar be so generic that we can represent our grammar through a language reference down to the T. Or we can say, look, at some point our grammar is proprietary, and we're going to have to write code that's specific to this grammar. And even though we have things within our language reference that allows us to easily expand our grammar, this grammar of statements here is more of a structural thing. Our types, these aren't structural. These are options, right? We have three different types we have in our language right now, and adding a type dog to our language would be pretty easy through our language reference. But changes that are happening to the structure of our grammar, that is, if I add a brand new thing called a dolphin statement, it has a brand new syntax, I'm going to have to go in and make major modifications to my syntax, to my compiler, correct? This isn't something I can just quickly make a little change in my language reference and expect the compiler just to catch up. I'm changing structural elements. That makes sense? So is it reasonable for us to say, oh, we know we're looking at a type statement, therefore we know there's two of them, we need to go one step further. Is that unreasonable? I think we can look ahead one. So if we're looking at a type, if I'm looking at a type, we know it is one of two possibilities. Okay? So we need to read in one more token. Currently, we're inside of a loop that's going to go through all of our Lex tokens. It occurs to me maybe this isn't the best way to handle this. Well, I'm currently inside of a loop that says, give me all the tokens one at a time. I just read in one of the tokens right here, and I've decided, oh, because I read in this token, I really need to get the very next token before I spin back up and get my next token. Does that make sense? Would it be helpful for us to create an object around our Lex tokens to give it kind of like a Pez dispenser? We've all seen those, right? The Pez dispensers? They still sell those?
Yeah.
Okay. So something that allows us to easily peel off the next token. What would that structure look like? It would be a stack. You've said something intelligent so far, Joey. Well, now let's take it a step farther and see if he really knows why it's a stack. What are the functions that a stack provides for us? And? Peaking. Would you have gotten that?
No.
What's the difference between popping and peaking?
You just look at one without taking it off.
Okay, it's an important distinction.
Peeking is look, don't touch.
That's how you stay out of jail.
Is that a phrasing? I think that's like an inverse phrasing. Right.
Well phrased.
Well phrased. Okay. So having said that, sometimes we want to actually remove a token from our list of our Lex tokens, right? Sometimes we just want to look at the next one. We want there to be a distinction there, correct? So what we're going to do is we're going to create a class. This guy's going to be called LexPez. All right. Now, if you look back at our source reader, our Lex tokens is just a linked list, right? Right here. It's a linked list of strings. So we're going to have inside of LexPez, we're going to have private linked list of strings, Lex tokens. We'll have our constructor public LexPez. We'll take no parameters, and we'll set Lex tokens to be a new linked list of strings. Okay. And wants us to import java.util. All right. Now, we need to have the ability to add tokens. to our, we need to have the ability to add lexical tokens to our linked list. When we add to our LexPez, are we pushing? Are we pushing onto the LexPez? Say this again. Who's Dr. Cario, for those of you who don't know who he is? When we add our lexical tokens, we're going through our tokens, we're lexically analyzing them, then we want to put them into our linked list. How are we adding them? So the very last, is that true? See, this is where this guy truly is a Pez dispenser. Because the Pez dispenser, we put the cartridges in the bottom, right? Well, we take the thing out, then we put the things in. So we don't feed it one at a time and push the other ones down. Correct? All right. So when we add a token, we're always adding it to the end. Because we want the very first part of our syntax to be the very first Lex token that we run into. This guy's going to act like a queue when we're adding tokens to it. When we're taking tokens out of it, we're going to treat it like a stack. What do you mean, can we do that? We're writing our own data structure for it. We can do whatever the heck we want.
Well, no, I thought you were just using the basic. You messed up.
So we're going to say public void add Lex token. This guy's going to take a string LT as a parameter, and we're going to take this dot Lex tokens dot add and adds it to the end. So I'll add LT. So this is how we'll add them to our list. All right. Now, before we do anything else, we want to go back and we want to update our source reader to, instead of dealing with a Lex tokens thing here, we want it instead dealing with a private LexPez Lex tokens. Okay, so there's my LexPez. Now, LexPez has something called add Lex token, where currently every single time we add something, we're just calling add. Correct?
Yeah.
It doesn't like it because we haven't actually built our. So Lex tokens is no longer a new linked list. Now it's a new LexPez. Okay. Now we get down to some regular errors. All our errors should have to do with adding. Lex tokens.add, Lex tokens.add, Lex tokens.add. So we can change a bunch of crap here, or we can just say LexPez has a method called add, which always adds to the end. That make sense? Well, we have our errors because we can no longer iterate over Lex tokens because it's not a linked list.
There's tomorrow. No, I'll fast it up way too fast.
What? You can't see.
He ran off again.
He ran
Right there.
Just click on the little red things on the side. Just freaking do it. No.
Where-
You're doing that purposely, aren't you?
Where's our error?
Scroll down.
No, click on the red. Click on it.
Let me click here.
Okay.
Size and get.
We don't even need this. This just prints out all of our tokens, right?
Is that what the error you get?
Huh?
We must not need that line.
Well, it's true in this case.
Fine.
Yeah, this was just our proof at the end of our lexical analyzer that we truly read everything in.
No, we didn't.
Okay. And then our last problem is down here. All right, so we want to go through our LexPez, and we want to pop something off our LexPez. So we're going to give a public string pop. And what's this guy going to do? He's going to return this dot Lex Tokens dot remove. This retrieves and removes the head of the list. Okay. So pop will literally remove the very first thing from our linked list, and then we're going to return it. So it will no longer be on the list. Make sense? All right, so there's our pop. Coming into our source reader again. Let's get rid of this loop for a second. We'll rewrap it with something here in a second. So we're going to say parts is equal to this dot decompose Lex token LT dot. I'm sorry, it's not LT. It's this dot.
How is there an error in a comma? It's a comma.
It thinks it's like a spelling error.
No, it's why? Dude, clean your code. You can only iterate over an array for instance of child.
Lex tokens. Okay. Yeah, that for each loop. The for I just needed to find the name of my things again. Lex tokens. I was too lazy to scroll all the way up, so I just decided to undelete stuff until I saw what I needed. So this is Lex tokens dot pop. So we'll go ahead and get the very first element. Shut up. Get the very first element from our list from our LexPez by popping it, and then we'll get the parts of that. All right. If I'm in here, if I have type, I know it's one of two things. I want to know what the next thing is. So now I need to peek. Does that make sense? So we're going to go into LexPez. Public string peek. And this guy's going to return this dot Lex tokens dot get first. This returns the first element in the list, but doesn't remove it.
What does get do?
Huh? Get like gives us the, it's like saying an array AR at bucket 5.
Okay.
It gives you the value there, but doesn't actually remove it from bucket 5. Okay? So now we have the ability to peek.
Yikes.
All right.
No, there it goes. I do save it. No, save it. Just command S. Probably will work.
All right. So
Is this sorcery?
now we need to peek at the next token. So I'm going to go ahead and I'm going to give myself a string called temp, just for right now. We're going to see that this isn't the exact way we're going to end up doing this, but for right now, this will be good enough. Temp is equal to Lex tokens dot peek. All right. So now we have the next token, but we haven't actually removed it from our list. Now we know we're either looking at something that is an identifier or something that's an assigned expression. Does that make sense? How would we know if it's an identifier? Be one of those guys. Correct?
We do the same thing if
So if it's an ID, we know it's that version. So rather than splitting the, go ahead.
Did we have to do this string temp thing, or could we just say is equal to Lex Tokens.peak?
Could say what is equal to Lex Tokens.peak.
Well, I'm assuming we do the same thing if Lex Tokens.peak is equal to.
Well, Lex Tokens.peak is a string. He's not a string array. So I mean, we could keep it all compartmentalized here, if you prefer. So maybe we say string.
Oh no, not like that.
String array temp is equal to this dot decompose tokens Lex token peak. That'll get us the parts. Then we can say if temp at bucket 0 dot equals ID. That's what it'll be, right? Like this. So if it equals ID, we know we're dealing with that type of type statement. That is type identifier semicolon. Else, we're dealing with type assign expression semicolon.
Would we do else if and then else there's an error? Or would
Sure.
we-
Yeah, that's fair. That's fair. For right now, let's just assume our code is syntactically perfect. So we're only solving one problem at a time. Okay? So if we make it inside this if statement, that means we're looking at a type followed by an identifier followed by a semicolon. So now we know the kind of guy we're dealing with. So we need to now build a tree. How will this tree work? This tree will kind of be like a fill-in-the-blank tree, won't it? We already know the exact structure that we're expecting. I think what we're going to find here is we're actually going to build recursion into our tree structure. And we're just going to start throwing things in the tree, and it's going to kind of drip down through there, building new trees as it goes. Go ahead.
Isn't a type assign expression also expecting an ID?
An assign expression, yes, would be expecting an I. Oh, actually, hold on. That's actually a very good point, because we did not. We don't have a special syntax for a. Well, no, we don't have a special lexical token for assign expressions. It's just going to be a bunch of identifiers and things like that. So the first part of an assign expression, you're saying, will always be an identifier. Therefore, the fact that we have found an identifier right here really isn't enough to know what we're actually looking at yet. So we need to keep going. What's going to come next?
Either a semicolon or an assign.
So we're either done or we need to go further in.
Yeah.
If we're looking at a type, if we're looking at a type statement, do we know for a fact, assuming we're making the assumption this is perfect syntax again, do we know for a fact that there will be 2 more tokens, at least? So we know that after that we could call Lex Tokens.pop twice, correct? The first time gets us this identifier. We know it'll be an identifier, assuming perfect syntax. Whether it's an assigned expression or not, it'll be an identifier. It's the token that comes after that we're most interested in. The guy that comes after that does what? It's either going to be a semicolon, and if it's a semicolon, which of these guys will it be? Reserved? Reserved will be our semicolon, right? Or it'll be a what? If it's not a semicolon, it would be a what? It would be an assigned expression, so it would probably be an equal sign. Won't that also be one of our reserved words? So, doesn't matter what kind of type expression we're dealing with, it'll always start off with a type, followed by an identifier, followed by a reserved word. The question is, which reserved word is that to tell us whether or not this guy is our first kind of type expression or our second kind of type expression? How do I access that next token? Well, remember, peek does not actually remove it. So I could call peek 30 times in a row and it will always just give me the very first thing. I don't have that method. Say this again. We could pop then peek. We'd have to preserve that token and come back to it. Correct? I'm going to say, why don't we write let's create our peek, and we'll stop right here. Just let me do this last part. We're going to write our peek such that it takes an offset. And rather than getting first, we'll get that offset. So if we send it an offset of 0, that'll get first. We send it an offset of 1, it'll peak at bucket 2. Does that make sense? Yeah. All right, so here, I'm going to put a little note here. Finish implementing this. That makes sense? This will allow us to peek a couple elements forward if we choose. All right. I will see everybody on Wednesday. For those of you who are in senior seminar, you should have got an email from me today. Tomorrow we do meet and have everybody give like a little 3 to 5 minute kind of update on where they're at. You can use a PowerPoint if you want, or you can just stand up here. It's your opportunity to either A, tell us how you're doing, or B, embarrass yourself in front of your peers by saying I haven't done crap.
Oh, great. I'm glad that option's there.